bars, but one couples to one, so there's also a complex length. So this guy will, like, this guy, its holonomy is L hat, and this guy's holonomy is L hat star, and so you want both plus and minus spin to couple to both L hat and L hat bar. It's
I see. So given L hat, you couple to both plus and minus.
Yeah.
And then L hat star, it's like that.
Yeah.
If you had a scalar, would there be no plus minus?
Yeah, if you had a scalar, there'd be no plus minus. So in some sense, this is, yeah, this is double the answer of the scalar.
It's basically the fact that the little group in 3 dimensions is U1. So each representation is 1 dimensional, but CPT makes you pair.
Yeah. Okay. So this is where we got to last time. I claimed that the one loop determinant of massive spinning fields labeled by some conformal dimension and the spin is given by this Wilson spool formula, where you sum over conjugacy classes of primitive geodesics in the quotient group of the manifold that defines this manifold here. The connections AL and AR are determined from the frame and the spin connection in the normal Chern-Simons gravity dictionary. And I take Wilson loops that wrap the cycle inside that conjugacy class. The representations here are lowest weight representations of SL2R with their lowest weights determined from the mass and spin in this way. And then this integral over this alpha parameter here is over a contour in the alpha plane that wraps the real axis tightly so that it picks up all the poles at 2 pi in. And so what this does is it implements a winding around each primitive geodesic of this conjugacy class. Sorry, each primitive geodesic that appears in this sum over conjugacy classes. And importantly, because I'm working with hyperbolic elements of SL2C, all the other poles that could appear from the characters themselves appear off the real axis. So they appear places like here and here. And so this winding, so this contour integral really only does pick up the winding. Now, that's not always going to be the case in every other situation that we've developed this Wilson spool programs. For instance, maybe if we don't get to it today, then I'm happy to chat in the afternoon with anyone about the sitter. The sitter space has more interesting pole structures, and it's important to keep the contour as opposed to sum to get that pole structure correct.
You tell us later, but I mean, both cases you have SL2C in the sense that once you go to Euclidean EDS3,
yeah.
But somehow the fact that it's a different hyperbola or something means that in de Sitter you get these extra.
Yeah, it's more like the nature of the characters here. So yeah, it's the nature of the characters. Here you get these cinches, and then in de Sitter you're going to get signs, and so it puts.
Because you're doing SO4, you're just doing a sphere.
Exactly. Yeah. Okay, so the first thing I want.
My understanding is he's just doing a partition function of a scalar field on S3.
That's right. For de Sitter, it'll be a scalar field on S3.
Is there a physical interpretation?
What'd you say?
Is there a physical interpretation for these alpha poles, the poles that you get from the character?
From the character themselves, yeah, that's a good question. If I had a good physical interpretation, I think it would resolve a lot of various tensions I have of where this program should go. So I don't. For these, the poles coming from this measure, that is very clear to me and from a physical picture, because then this just implements this winding. But the fact that, for instance, on S3, you get these extra poles means that it looks like the whirl lines are more than just winding, and I'm counting 1 over n, because in that I would get the wrong answer, right? There's something interesting going on with the pole structure that I was saying there's some slipping modes or something. Maybe there's a nice way of thinking about that, but that connection is like not clear in my head. Yeah.
Just to get this right, so maybe I was thinking wrong. So if you take the second order gravitational path integral for De Sitter space and you say, okay, I have to do it on S3,
Yes.
then when you write it in the first order formalism, you recast it as a SU2 process?
Yes. Yes, I recast it as an SU2 cross SU2.
Not as the SL2C.
Yeah, but I mean, whenever we quantize these theories, right, we need to complexify the connections anyways. And so, in truth, we're always working in the complexified group, and so the complexification will be SL2C. But I want to organize it in terms of SL2, SU2 cross SU2. Yeah.
I thought it was SU2 cross SU2, no complexification, right? Just
Well, the levels, for instance, are complex in that case. The levels of the Chern-Simons theory are complex. Okay, so the first thing I want to do here is I want to compare this to known results. So, for instance, there's a famous paper by Guillaume, Maloney, and Yin, computing. Yeah. Oh, sorry. Just which two boards? Ah, okay. But this one's okay. Cool. I assume that was the case, but I don't know how the. It's a bar. Ah, fantastic. Okay, cool. Well then, I'm going to make a comparison to the results of this paper, which is a set of one-loop determinants evaluated on different hyperbolic spaces. They're primarily focused with scalars and spin 1 and gravitons on thermal ADS and other simple quotients, but the machinery there, it very much applies more generally and it gives us something to match to. So the first thing that we'll do is we'll just evaluate these as SL2R characters, which we had written down before. And as I was alluding to earlier, because every element of this group is hyperbolic, then these taus have poles have non-zero imaginary part. And so the poles of these characters always lie off the real axis. And so doing this alpha integral is trivial. And what we have is
this is the Guillaume, Maloney, Yin answer, is it?
Yeah. This is we're going to try to land on that answer. Yeah, this is a comparison too.
And the difference seems to be close. They have these characters, guys.
They do have these characters.
They have these Wilson spools.
Yeah, that's right.
They're the same thing, right?
It should be the same thing in the end. Yes.
No, but I thought this Wilson spool was the trace of wasn't it exactly like that?
Yeah, these are exactly the characters. Yes. We're going to simplify this down to the product, to this determinant that they write down. Sorry, maybe I misunderstand what the question is.
Are you rewriting your formula?
Yeah, right now I'm evaluating my formula.
No, confusion was we thought you were stating Guillaume, Maloney, Yin.
No, I'm trying to make contact to that. Yeah.
When was this paper? Guillaume, Maloney, like 15 years ago? Or?
Yeah, it's ancient history. So this is a tau bar. Okay. And then we had this expression for the characters. I will just do all this simplification down, but what we can eventually recognize is that the exponential of this spool takes the form of an appropriate CFT character. And this is the answer that we were trying to compare to. So again, this was written down for spin 1 and 0, 1, and 2, but naturally generalizes for any other delta in spin.
Is it just a Virasoro character, right?
It's just a Virasoro character, right?
Of some given time.
Yes. Yeah. Okay.
This is a Kimbo with Maloney, and that's just a Virasoro character.
Yes. Yeah. Now they arrive at this through heat kernel methods.
Sorry, the Virasoro character,
Yes.
I mean, there is also this product over gamma zeros.
Yeah. So good. It's yeah. This isn't. So,
This is not just harmonious.
yeah. If it were just this, then this would be the Virasoro character for thermal ADS. And what we have here is we basically have a thermal character for thermal. Sorry, a Virasoro character for thermal ADS for each primitive cycle.
Oh, I see.
Again, this is the answer that they arrive at from after heat kernel.
So the model was still there, that at every primitive cycle behaves like thermal ADS.
Yes.
And then we have the answer.
Yes.
Sorry, very elementary. Why are you expecting the Virasoro character? I thought Virasoro character was wherever you have rest with boundary gravitons. Whereas you had multi-particle. Oh, the multi-particle is still there.
Yes.
Where is that? Multi-particle.
So that would come from expanding out this one minus.
I have the same question. But I have the same question. I mean, you haven't included the effects of boundary gravitons, right? Because I thought when you evaluated, you kept internal geodesics, but not the boundary effect.
Sorry, but I'm considering the matter one determinant. This is insensitive to the boundary gravitons.
Yeah, but the way I would say it is that you made each mode a harmonic oscillator, and you've taken a product of a harmonic oscillator, so you multiply.
Yes.
So what he's done is there's this character, right? It's one particle character. For each state, he's made it a harmonic oscillator. Yeah. So one minus that, and then product of that. So
Yes.
that includes multiply.
Yeah, that is just a platistic.
Yeah.
That formula is just a platistic log of that, right? 1 over, and that's the standard
Yeah.
platistic log of it.
So it will be many Virasoro characters.
Yes.
It's many ways.
Many, because each number
Sorry.
of particles is its own Virasoro.
Yeah. That's yes, that's true.
Sorry, but Virasoro
And then
symmetry
the-
isn't even.
Yeah, he's not even on the boundary.
Yeah, there's no
Each of these will be a primary for
Yeah.
So this is just the primary.
the SL2R characters. SL2 whatever.
This is just the primary.
Yeah. Yeah.
Yeah. It's, I see.
You need to trace it with boundary gravitons and then it becomes.
Okay.
Very platistic log, right?
Yeah. That's how you type it.
So it's just done the
Multi-particle.
particling. That's what it's done.
Okay, so now I want to relate this to the Selberg trace formula, and which can be seen as a way of arriving at this without talking about quasi-normal modes or world lines, and then after that I'll talk about world lines.
You see sorry, just to say that
Yeah.
the top line was the platistic log. This is like, that there were two ways of doing multi-particle. One up in the exponent and one downstairs. This is the downstairs, that is the exponent. That sum over n was the platistic. And here he's just written the downstairs.
Sorry, I should use persistent.
Bose exponential. Bose exponential.
The Bose.
Bose exponential. Platistic, I don't like that word.
Okay, are we happy? Okay, so a one-line explanation of what the Selberg trace formula is, in case you've never encountered it before, or maybe you did and it's slipped out of your head, is it's something that relates the spectrum of Laplacian on a hyperbolic manifold So I'll call that somewhat schematically by this lambda m. M here is like a mode number, not the mass. And it relates it to the spectrum of complex lengths on that manifold. It could be 2 dimensions, it could be 3 dimensions. Actually, it could be probably any number of dimensions. I know it best in 2 and 3, but yeah.
And so, when you might refine some of this, again, in your second line, you take some notion of primitive geodesics or something, and
Yeah.
you look at what values the lengths take, or when you say spectrum of
Yeah, so good. So right. So I would take, yeah, in this case, I would take all primitive geodesics, and then all those primitive geodesics then sort of, in some way, generate all the elements of gamma in the way that every element of gamma can be written as a primitive to some power, at least when it's torsion free. When it's not, then I just have to consider all the conjugacy classes of gamma, right? However, for these torsion free ones, I can consider the primitive ones. And then I look at the complex lengths of those primitive ones. Of course, there's still an infinite amount, but there's some algebraic way of generating these.
and spectrum just means the values, the complex
Yeah,
state.
yeah.
I was fixing up that double arrow means what? The Newton relation.
It's a relation between functions of one thing to functions of another thing. Yeah. And so actually, more specifically, for a smooth test function,
So Selberg trace formula, just to get orientation, allows you to find the whole spectrum or just the determinant?
I'm going to state what the precise thing is. I think it's going to imply that you should be able to isolate the whole spectrum,
Okay.
but so the precise statement is that if I have some smooth test function R to R, and I can also construct its Fourier transform, H tilde, so this is the Fourier transform of H. So the summing over the spectrum of the Laplacian plugged into the Fourier transform of this function. So you might be able to, by judiciously choosing these H's, be able to use this formula to isolate the spectrum on the left-hand side. We're going to use it to talk about the determinant, though. Okay, so here the L without the hat is the real part of the complex length, right? And then the theta is the twist, which is the imaginary part of the complex length. So this is the statement of the Selberg trace formula. So it relates functions of the spectrum of the Laplacian to functions of the complex length in this way.
The many up here on the right hand side, theta gamma is something you associate with every cycle, is it?
Yeah, it's twist to that cycle.
It is the twist.
Right, so recall that this complex length is, its real part is the geodesic length plus I times the twist.
And what is S? S is
S was a spin, right? So this will be a Laplacian acting on some symmetric traceless.
N gamma. L gamma by N gamma.
So recall that, recall that for every element of this, at least for these torsion-free groups, has a homotopy invariant, which is an n gamma. So it will be some primitive element gamma 0 raised to a power n gamma, which is it's a homotopy invariant. And so if you like, then this sum is the same as summing over primitives and windings, yeah. Okay.
And in your formula, when you had an n gamma, you had to multiply the length also by n.
Yeah, that's right.
Here, there's no multiplication by n.
Well, the length of this guy will be.
Oh, that automatically.
Yeah.
Yes.
Do I want to use this board? I'll use this board. So to make connection to the determinant, we're going to choose H to be Gaussian.
So can you see, is it possible to say the idea of why this is just the...
I don't know. I think there's a lot of people who are very interested in why the Selberg trace formula works. In some sense, Shiraz said it probably best yesterday after everyone had left, which is the Selberg trace formula is probably just a restatement of the world line formalism working. So maybe it'll be a bit clearer when we talk about world lines after this.
Saddle point approximate.
Yeah.
So it's true for all H, right? For any H.
Yeah, that's the amazing thing is it should be true for all smooth test functions. Yeah. Okay. If we choose H to be a Gaussian, then this will allow us to look at things like this, e to the negative beta lambda m, which then allows us to compute log debts in the following way. Sorry, this was Gaussian. Yeah, sorry. I was a bit not careful. The Laplacian is like is lambda squared. And so, yeah.
Is one way of thinking of the Selberg where you look at a particle on whatever your space is times time and compute its partition function. That will have all information about the spectrum, right? Because that would be trace over that spectrum. And then you try to formulate that well line particle. That would have windings here, but would also have some windings in time.
You don't need the time. You're just looking at the particle, world line particle
on the hyperbolic manifold, yeah.
But I want to get all of the spectrum.
You get all of it.
I was thinking the way to get that spectrum is to have a trace e to the power minus beta.
Exactly. And that trace is exactly that's the
So, but I think what Shiraz is.
And then you want trace e to the power minus beta Hamiltonian. Therefore,
but that trace is the time along the world line.
Right?
Time along the world line increment.
You're right. Yeah, this is just target space. You're right, absolutely. Thank you.
Yeah, in some sense, this beta is going to play the same role as the world line parameterization.
So, I see. So, just length of that.
Yes.
Of that circle.
Yeah.
You just need that length.
How do you get the spectrum?
You get an inverse Laplace transform.
then it's still a plus.
Right? Because if you know the partition function, you know the spectrum. There's enough information.
As a function of some parameter like mass.
Yeah.
Yeah.
No, can you just integrate it?
So why can't we just do a separate problem?
Yeah. So, sorry, yeah, Shiraz, Shiraz, you want to do this part without doing the integral over beta, and think of this as a function of beta.
Yeah,
Yeah.
right. So I'm just trying to be a mathematician and get Selberg trace form.
Yeah.
Okay, so if I want to know all the eigenvalues, what I will do is compute a partition function. Right?
Compute a partition function
Trace.
with some time, right? With some time.
With some time. So as Onkar said, the way to do that is in quantum mechanics, you just when doing sigma model, quantum mechanical sigma model in this space. Okay, so we make the time periodic with some periodicity beta, but I keep that. I don't integrate it. I keep it. So then I get a function of beta from which I can pull out the spectrum. Right. So this is if I were trying to derive this is how I would do it. So,
I think physics presentations of this formula usually follow.
do that. Excellent.
The zero color simple minded thing that you put in the Shunda parameter and then you start interpreting it as a word.
Yes,
Yeah. You know,
that's, but here, I mean, that includes the integration over the swinging parameter, right? I think if you want the spectrum, you want to, yeah.
Yeah, but even without any Shunda, suppose you have a sigma model on this. Its spectrum, its Hamiltonian is the spectrum you want to compute.
yes, I agree with that.
So you just take a sigma model and put it at finite.
I agree with that. What you're saying.
Yeah. So that's from get to go is a finite, is a world line model.
And then it has to localize on units.
Then you have to show that it does its own. But at least you got the sum of world lines, right?
Yeah.
Yeah. Okay. So this integral can be done on the right-hand side here. And evaluates the following. I'll explain some things in just a second. Okay, so there's this term here, which when you evaluate is going to give you polynomial divergences in epsilon, proportional to the volume of the manifold. If you like, this comes from contractible world lines, the ones that can shrink to zero size that Shiraz mentioned before. And we're going to take the perspective that these can be dealt with by choosing some renormalization condition. Here, at this point, we're just going to minimally subtract them. However, it's this portion here that's more interesting for us. Nu here is just the normal nu that we encounter in ADS CFT. And we have, again, this summing over primitives and then the complex lengths. And then it's from here that we can now make the connection because we have this map from complex lengths to holotomies of the Chern-Simons connections. And happily, we see that this now takes the form of a numerator and denominator of an exponential and a sinh, which are indeed these SL2R characters. I've done the beta integral on the right-hand side.
Sorry, so when you said log, then that's just an identity, right?
This is an identity, right? So this is identity, this part here. Then I've said I'm going to take this, use Selberg trace with H as a Gaussian.
Right.
I plug that Gaussian into here, and I do the integral over beta.
Oh, and the result is written there.
That result is written there.
The beta was appearing where? That H.
Yeah, H here, so maybe I went too quickly here. Yeah, so the first step is I write log Z is a Schwinger parameter, so d beta e to the negative beta summing over all the spectrum e to negative beta. And then I say, this guy I can think of as H tilde of a lambda. I want to use Selberg trace to write this in terms of H of L. There's a beta appearing in the H. And then now I take this right-hand side and I integrate d beta, all the stuff with H beta of L.
So that is exactly the quantum mechanical partition function you were talking
Yep.
about. Some of them they publish.
Yes. Okay, and so now we use this map from complex lengths to holonomies. As far as I'm aware, yes. Yeah.
Because, I mean, once you're away from that, you might worry that the saddle point approximation rate.
Yeah. I'm also unaware if the Selberg trace applies over higher than 3 dimensions. Or,
okay.
This is genuine ignorance on my part. It may or may not. I don't know.
That's where it works.
Yeah. Again, I know it best for 2 and 3 dimensions.
So higher dimension hyperbolic also opened over, right or not?
It's completely outside the realm of my knowledge.
Higher dimensional hyperbolic also overflows. Then, I see. Or maybe another way of saying it is what that thermal ADS, it was just representation. Some open areas. But that will always be. And some high dimensional. If the thermal ADS part is there some angle of thermal ADS in it? Obviously. Then
Not in the sense that you can get everything.
yeah, I think you can, because it's just replication. Yeah. Then if you say, basically this will come into this.
But was it important that your one-line path integral was 2 loop exact or something?
That's something that I think will only hold in 3 dimensions. Yeah.
Will only hold.
Yeah.
That wasn't, it seemed a bit of a miracle to me.
Well, for thermal ADS, that in fact is just representation.
Yeah. So here it seems like it's a miracle for these quotients, but it sort of breaks down into a couple of small miracles in a sense. So the first small miracle is that I can think about this sum over all the conjugacy classes as a sum over the primitive conjugacy classes. And then since the primitive conjugacy classes just now just reproduce everything with some power, I can now think about that each primitive conjugacy class as being like thermal ADS. And so the whole thing breaks up into some of thermal ADSs, but it's a thermal ADS for each primitive. But now, as far as that calculation is concerned, it might as well have been thermal ADS. And that's when I know that it's 2 loop exact. Yeah.
Is the spectrum infinite dimensional or finite dimensional?
It's going to be infinite dimensional.
Both these.
Yes.
So can you think of that formula as some Poisson resummation kind of thing?
It's very much like a Poisson resummation.
Over the Fourier transform,
Yeah.
that's exactly equivalent to that.
Yeah, it's a little. At least has a structure very much like a Poisson resummation, especially since this is a Fourier transform here. Again, I think the right way to think about it, and if you want to make that precise, is this sigma model point of view, where I think about this as world line time, and then is the thing about this in the sigma model language, right? It's a world line propagating on a manifold.
Yeah, exactly.
It's a world line propagating on a manifold. Okay, which maybe now I will get to if we're.
What is this first and the second part?
What'd you say?
Like in terms of this Poisson resummation,
Yeah.
can you identify on the right hand side what is the first part and the second part?
No, I don't know. I don't know how to make sense of this in terms of the Poisson resummation. Maybe someone a bit smarter than me can make sense of that. But in my head, this term here, so I very much organize this entire calculation, and both conceptually and also in calculationally as a restatement of the world line quantum mechanics. And this, in that case, the fact that this is proportional to volume is very clear because it's coming from things that are just contractible loops, and there's a volume's worth number of those contractible loops. And this is why also they're divergent, right? And I should renormalize them in some way. In some sense, all the robust topological things that depend upon the complex lengths here, are finite, and they appear in this part of the sum. So maybe if you want, the speculative way of thinking about this in terms of Poisson-Ries summation, maybe the Poisson-Ries summation is divergent at the high ends of the spectrum, and this is the divergent part that you have to deal with and subtract off maybe, or at least renormalize. And then there's some finite pieces that are robust and universal. Yeah. Onkar, how much time do I have?
So we have this loop till about 1.
Ah, perfect. Yeah, okay, great. Then that should be enough time. Well, I think that should be enough time. Okay, so now I want to think about this in terms of world lines. So this will make more direct contact to this beginning intuition that we had. That this object is an effective avatar of particle world lines. And so the first place we're going to start is just the expression of log z as a world line path integral. And I'm going to stick to scalars here because actually I'm a bit confused on what a spinning particles world line is, but we'll work for scalars in this section. If you
I mean,
what?
3 dimensions, there are no degrees of freedom.
No, on the
I said, yeah, I don't know how to think about a spinning particles world line, even in 3 dimensions.
I don't know what you were saying, but there's no polarization. There are no options.
Okay, I see. I mean,
There's a plus and minus.
You have to introduce
Because there are new states.
Yeah, okay.
But there's a plus and minus, right? There's the plus and minus that I have to choose for the spin.
That's one, one particle, the other particle. I mean, this one. But what I'm saying is you can look at each of them separately.
Mm-hmm. Okay.
Isn't that what you were doing? I thought when you
No,
were
actually,
when you were saying-
yeah.
I mean, in some ways, yes. The fact that they appear is just a sum of plus and minus there, then that's.
Actually, maybe I'm getting confused. Now, what I was saying was this: that suppose I take a fermion in 2 + 1 dimensions.
Mm-hmm.
Now, if I know its momentum, I know its polarization by Dirac equation. Because the polarization is 2 × 2, and if I give you that it's positive energy, then I just know the polarization. So there's no ambiguity on the
Okay. Yeah.
I was just imagining that you're doing a determinant over now column vectors, spinners or column vectors or stuff like that.
It could be that there is some auxiliary, but you should get a new state in the universe.
Okay, yeah, that's how you look at that.
Yeah.
Yeah, and given that at least all these should be thought of as exponentiations of single particle states, then I'm happy with the on-shell argument there.
This is why most of the duality works.
That's right.
Yeah. So in fact, if
Okay.
It doesn't depend on P and this one, unless
I would be very happy actually if at some point I could figure out how to just work directly, incorporate the spins directly into this. But so I'm happy also to discuss this afterwards. But for right now, I'm going to stick to scalars. Here's the worldline path integral. So this is an integral over all paths with initial and starting points the same. Here, tau is the worldline time, and the extent of that worldline time is a parameter I call beta. And this integral d beta over beta has sort of two roles in life. And one role in life is that it's the Schwinger parameter that implements the log. But another role in life is that it is actually a gate. It integrates out the redundancy in choosing the length of this worldline time. Okay, so the first thing that we're going to do, so this is paths taking place on our manifold M, and we're going to uplift this to hyperbolic space. Yeah.
In going from J sub e to the minus beta h to here, one has to often worry about these operator ordering ambiguities, and then those give some counter terms.
There is a counter term it's going to be something that I had planned to sweep underneath the rug. There's an ordering ambiguity. There's a counter term here. It's a constant shift that it would have been a very annoying detail to keep track of. But it's in our paper if you want to see it there. Yeah. Okay. So we're going to pass to worldline on H3. So each closed path on M will lift to an open path. Well, maybe I should put an asterisk. If I'm not thinking about the contractible closed paths here, that gives this divergence. If I'm thinking about the non-contractible closed paths, then each closed path on M lifts to an open path. On H3. And we're going to call that open path X tilde. And we can choose a fundamental domain such that we can set the initial part of that closed path in that fundamental domain. And then the endpoint of that path will be some element of this quotient group, which will lie in some conjugacy class. And this guy will lie in the fundamental domain that I'll call F sub tilde here. Okay. So, yeah, this is so far so good. I'm going to call this entire thing on the, so I'm a bit annoyed at myself for jumping back and forth, but this log z of the one-loop determinant is an entire worldline path integral, so I'm going to write z WL here. Yeah.
Yeah, so M is some quotient of H3 by some discrete subgroup.
It's a quotient of H3 by some discrete subgroup, yes. Yeah.
So Jackson,
Yeah.
at some point, did you show us that the Sedgwick formula gave your formula?
Yes, yeah. Yeah, that was done. Yes, it came down to I did this integral and I saw that all the non-contractible stuff, the non-UV divergent stuff, takes the form of SL2R characters, and then I just noted that there was this map from complex length to holonomies.
And now you are trying to get another derivation of your
Yes. Yeah. Yeah. In some sense, I'm trying to maybe put some more meat to the Selberg trace part of this. Yeah, so these may or may not be, they're probably not independent derivations, right? Given that I think the Selberg trace is a restatement, but in some sense it's a more intuitive way forward. Okay, so then there's this trick. I'm just going to call it the GMY trick because this is where we learned it from, and this is the trick that I mentioned yesterday, where we replace this summing over elements in a conjugates class and this summing over paths that land in F or land in gamma F. Let me write it as. And we replace this with the following. We pick a representative. Sorry, my handwriting's terrible. We pick a representative of gamma bar, and then we integrate over x's that lie in the centralizer of that gamma bar. And so here C is of the representative. So for torsion-free gammas, each C gamma here is an infinite cyclic group, which means it's generated by a single element, and then it's just raised to a power.
Sorry, just a quick question.
Yeah.
If you have a sum over a group and you want to write as sum over conjugacy classes,
Yes.
Is it that each conjugacy class then must have a sum over these centralizers?
Yes.
How to see that? I mean, I thought it would just be that you have to sum over all orbits under conjugation, right? So
That's
the
right.
conjugacy class is an element, some representative, and an orbit under conjugacy.
Yes.
That you have to construct and then sum over all conjugacy classes. So that orbit sum, how is it the same as the sum over centralizers?
Let me think about this. Yeah, so these are the elements of gamma that can mute with this representative.
Yeah, so as far as the action, the conjugacy action of this commutant will be concerned, the gamma will just be fixed.
Yeah.
It will just vanish.
Yeah, that's right.
It will be fixed. Yeah, but then there will be other non-trivial things also which following from non-centralizers in the orbit.
Right. Let's see here. Where do these guys go? Yeah, so I think what I want to say is that sorry, let's see here. I don't want to say that we're integrating them out. Let me.
Volume of each.
Yeah, but
Number of elements that are.
no, but I don't think it's quite that either.
Exactly that. Yeah. Number. It will just be. And then since they are also the same, we could just that number.
Another thing will be if you do all the others which don't give you the same answer in the end.
Huh. They do. They won't because they group it won't.
No, I mean gamma under conjugation will not necessarily be gamma, right? It will be different.
Yeah, that's
It will
right.
be the same answer to the positive. Because it's group it won't.
Yeah, right, exactly. Right, you are right, yeah.
Is there some issue with the Alvin fold?
No, it's not that.
Number depending on which conjugate.
Yeah, I think,
I think that's it.
No, I think that must actually be the centralizers,
I
right?
thought within
Yeah.
the conjugacy class, he was wondering how the order would change. Okay, you should.
I mean, it's like the random one for you. The volume of the data.
Yeah, the volume, yeah, but not, that point is that not the full group, right? Because under some groups it's stable,
Yeah.
right? That's exactly the centralizer. So you can see that the centralizer will come in.
mhm.
Is it that the centralizer just appears as a number?
No, sorry, what we're going to end up doing is I'm going to write down, let's see here, I'm going to write down let me write down what the step after this is, and then I can try to disentangle this.
It's like the random one. The ideal values of the volume. That's like new ones. That's like it's basically gauge fixing.
I think in a way it is gauge fixing, but let me try to disentangle this in real time.
They're not really identified.
So you're saying you have to remove those that now. When you speak of the gauge,
Yeah, or it should somehow be the same.
yeah, but what you're saying is think of it as gauge. So every orbit comes. These things that switch your gamma should not be thought of as physically. No, they won't.
They won't be. No, that's what I'm saying. This makes it
No,
feel.
but then there's a question of whether you should add the number.
That you
Yeah.
should. Okay.
No, okay, so yeah. So what we've done here is we've replaced this with the fundamental domain of the centralizer, and then that fundamental domain of the centralizer is in copies. Sorry, we can replace that with the fundamental domain of the entire thing generated by gamma. But it's in copies of that, so we divide by this 1 over n here. So this is where we're going to get to. And it's this term that looks like now thermal ADS, because thermal ADS, the fundamental domain generated by this one cycle is just the uplift of the quotient of this torus.
So what is the role of the centralizer that?
Yes, so good. So let's try and work from here to here.
Why don't we do it in the case just of thermal ADS?
Well, in thermal ADS, it's a bit, you've already started here because there's only one primitive geodesic, right?
Yes.
And so there's only one thing to consider, and all these conjugate classes are just products of that one geodesic, right?
Okay.
So everything's in the centralizer, yeah. Yeah, exactly. So here it's important that you've broken this down into the centralizers. And I think I have to waffle on this and revisit this. because this is an important step. It's also the important step in this paper as well. But yeah, let me get back about what happens to the terms that don't commute here. I'm suspect that they indeed give the same answer in this formula, and so there's some form of gauge fixing where you're not considering them, but that's a bit waffling on my part. Yeah.
I was thinking that if you have this, let's say you're fixing this at the origin, right? And this guy's here,
Yeah.
the other guy's here, right? And under conjugation, what will happen is that this guy will move like this, so that this distance is constant, right? It will
Yes,
look
that's
the
right.
same, right? But you have infinitely many group elements to conjugate with.
That's right,
Right?
yes.
But the images are only these ones. And why is that? That's because there is a kernel, right? That those are the centralizers. They're the ones that do not change this.
Yes, that's right.
So in order to see how many images that you should have in a given this thing, conjugacy class, you have to mod up by the centralizer because that is the same image,
Yes.
right? So what should enter as a weight of each conjugacy class seems like the total group divided by the centralizer, right?
That,
Those
yes.
are these ones.
The one question is, should we be counting these images as distinct?
Yes, you should.
They're
Yes.
not just related by symmetry.
No, but to go back up.
They should,
That
this,
follow, you just have to
this would tell you that they're counted as distinct elements.
you have fixed the origin to 0.
No. I mean, here I'm sorry. I think this boundary condition is telling me all I need is that the boundary that this x lies within the fundamental domain. It's not a fiducial point in the fundamental domain. It's that it lies within the fundamental
Yeah,
domain.
that's what I mean.
Yeah, okay. Yeah.
Some fixed fundamental domain, right?
Yes.
Yeah. And then why?
I always think these two identifications would be related by one of the other identifications. But this identification and that identification are related by a second.
I think, yeah. So we can think about all the gammas within a particular conjugacy class as being homotopy equivalent gammas, right? And so in some sense, I think maybe this is coming into a definition of the measure, the fact that we want to consider all these as actually equivalent, but up to this issue about things that actually are left fixed, which are the centralizer elements.
One example. But
Yeah.
I mean, what you are saying here, that would mean that you just replace the sum over group elements
By
by
sum
sum
over
over
classes.
this class.
Yeah.
Yeah.
But there is a weight there.
Yeah.
Right? 1 over n gamma appears.
Yes. This 1 over n gamma appears here, but that's because we're now considering not just the fundamental domain of the centralizer. We're considering,
That's the winding.
yeah,
What is the effect of that centralizer happening? What was the effect? You know, here you wrote that sum over conjugacy classes, then there's some more images in the conjugacy classes.
yes.
And then they just went away, or what was the effect of that?
Yeah, I think what I want to say is that the image, sorry, the guys that live within a single conjugacy class are homotopy equivalent to all the other guys, right?
I see.
And so in some sense they're absorbed into this measure dx, but we still have to consider the elements in the centralizer for this issue they mentioned earlier, that they're left fixed underneath these images. So let me think a bit harder about it, and this is my intuition on where this is going.
But what is the label there? The F gamma F?
Yeah, good. So I have the fundamental domain of the centralizer element, or centralizer of this, and this is I can then look at the entire F that is generated by this gamma, right? So I have a particular representative of the conjugacy class gamma, and now look at the cyclic group that's generated by gamma, and this is just n copies of the fundamental domain of the centralizer. So I divide by this n here. And if you want to think about thermal ADS, it's like I have this symmetry factor from how many different ways it can wind around thermal ADS, and if I consider the entire cyclic group generated by that, then I need to divide by this 1 over n symmetry factor. It's like that. Okay. So now we want to do the actual path integral about this. Let me turn back to here. Right. So each term in this sum essentially looks like a word line path integral on thermal ADS now, which is the key thing that we're going to lean on. And is there, this is an eraser.
So there was also a factor of e to the power minus beta something.
Say again?
E to the power minus beta something. There was a factor.
Yeah, there's a factor with the mass as well, yeah. Yeah. Okay, so on each one of these terms in the sum, we can choose a hyperbolic metric that looks like thermal ADS. And then the effect of this gamma here sends T in phi to T plus L gamma and phi to theta gamma. So the T is like keeping track of the thermal ADS time, and then the theta is keeping, or phi here is keeping track of the twist. See here, so the fundamental domain generated by this gamma then, or the fundamental domain of this gamma, I want this generated or this gamma? I'll go with what I wrote. What I want is this. So T will take values 0 to L, theta goes from 0 to pi, and R goes from 0 to infinity. And I will also introduce coordinate Q, which I'm now realizing is going to maybe be confusing with the gnome that we had introduced earlier, but oh well. Cos phi. And R sine phi. Right. So the metric here very much, well, we can already see that if I take this metric and I use it and I plug into the action, that it's going to be something nonlinear in terms of Q. So it's not entirely obvious that this is just a solvable path integral. And so it will take work, right, to actually evaluate this.
From there, what did you do there?
Oh, I just worked in this variable Q, and underneath, after going around gamma, Q undergoes a rotation. It rotates by this twist. So there's a rotation matrix of theta, Q here. Okay. So what we're going to do is we're going to organize this word line path integral into loop expansion. So this is for each gamma appearing in that sum. And this W will have a on-shell term, which will be just the geodesic length. You'll have a one-loop term. You'll have a two-loop term, and maybe more. And amazingly, for the one-loop term, there's a canonical transformation that we can make.
Just harmonic oscillator.
Yes. Yeah. You say that like it's obvious. It took us a while to realize this. So, yeah. There is a canonical transformation that basically turns at least for considering the one loop part of this, the quadratic pieces of it into a term with L hat times 1h plus an L hat star times another h. These are not the same h's, but they're both harmonic oscillator Hamiltonians. And so the one loop term can be thought of as purely just the thermal entropy with energy spectrum of the L gammas, which then connects to this idea of the Selberg trace that the spectrum of this are the actual complex lengths. So yeah, I wanted to make that comment. So harmonic oscillators, and importantly, the spectra of those harmonic oscillators are complex lengths, which then should bring to mind our previous statements from the Selberg trace. Okay. So I had meant for that to be a somewhat surprising realization, but you had already hit upon this quite early on. Okay.
Sorry, the fact that it's a one-loop
Yeah. So we still have to worry about the two-loop piece. Right now I'm just showing that the one-loop piece breaks up into this harmonic oscillator type thing. We're going to deal with the higher loops in perturbation theory.
But I think Onkar was saying that it's got this U1, the symmetry.
Yeah.
So it looks like 2D harmonic oscillator. I mean, it's got a problem with the rotational symmetry. It's quadratic, so it's reasonable to expect it will be a 2D harmonic oscillator.
Yeah. So I'll just write down what this one-loop answer is at the end of the day. Okay, so that's the one loop answer. And you can roughly think about this as coming from the time part of the integral. And then this comes from the two harmonic oscillators, which were the Q parts of this integral. Okay, so we still have to incorporate all the higher loop stuff, which we would do in perturbation theory. And what's amazing is that this Z world line is two-loop exact.
As you said, the only two-loop effect is changing M to delta, right?
Yes. The only but there's a bunch of two-loop diagrams that all are non-trivial here. So these are the non-trivial two-loop diagrams, and I think right here this line here is the T propagator, and then this solid line is the Q propagator. So these are all two loop diagrams. Each one is non-trivial, and some of them are divergent. They have things that look like delta of 0, but the divergences will cancel, and all the non-trivial beta dependence here cancels. Or sorry, all the non-trivial length dependence of these things cancel, and all you're left with is that these sum to beta over 2. And so, indeed, given that the exponential of beta has an m squared, it just shifts the m squared there. Now, the fact that this is two loop exact, the simplest answer I have for this is that it's essentially a calculation of thermal ADS, and that as far as this particle that is traveling along the whirl line is concerned, it sees a geodesic that is just like thermal ADS. Essentially, the whole calculation is broken down into sum of thermal ADSs. If someone told me that thermal ADS had a one loop exact answer, I would believe it. A two loop may be a little bit strange, but again, the two loop is just shifting the mass to a conformal dimension. Now, we just had a grad student check the three loop diagrams and see that they're 0. I also did a perturbative analysis of the heat kernel version of this. You can also do heat kernel perturbation theory and see that things terminate at second order, and I went up to like 6 orders, maybe 5 orders, and saw that they remain 0. So when I say it's two loop exact, I mean to the degrees that we have checked and up to, I think, a fairly reasonable physical argument. There's also a paper by Henry Maxfield that also evaluates the world line quantum mechanics on ADS3, and he claims with very little fanfare that this is two loop exact. So you're also welcome to. The physical argument is that the thermal ADS partition function, or the world line path integral, should just be this character of the CFT. And there's nothing else that can appear there. And if I've just broken this into basically sum of thermal ADSs, then what else can I get? Yeah. But essentially, in doing this calculation, we were following this paper by Henry Maxfield. And that's from 2017. Okay, but this, indeed, the only role of this term is a shift of m squared to nu squared, which is m squared plus 1, and is gamma independent. And so what we find at the end of the day is that this world line path integral and Oncarv, to satisfy your previous question, in arriving at this answer, we also did have a constant shift that came from a normal ordering counter term. This is essentially the same integral that appeared in our Selberg trace formula.
We have understanding characters from like the one line path until the whole joint orbit.
Yeah. You would think so. Here, though, the target space of these world line path integrals are not necessarily, or not to the degree that I know, are orbit spaces, right? So they're propagating on some hyperbolic space. So there may be a connection there. It definitely smells like that, but not in a direct way that I know. Yeah. Okay. So log So this reproduces Selberg trace, and then also once we interpret these as characters and map them to complex lengths, gives us the Wilson spool formula. So I want to make a couple of comments that draw a comparison to this Wilson spool formula. But maybe what would be good? I'll erase some Selberg trace stuff here.
Jackson, I have a suggestion.
Yeah.
Since we have 20 minutes left, maybe we can skip details now and move to big picture mode.
Yeah, I think I'm trying to move to big picture mode right now, actually. Yeah. So essentially, when I say draw a comparison, I'm trying to put some words to these formulas that I wrote down. Yeah. So here the summing over the conjugacy classes arises from summing over topologically inequivalent world lines, or topologically independent world lines. We should call back this notion that we are summing over topologically independent Wilson loops. This exponential damping here, we can think of as being the exponential damping is like the on-shell piece, or the classical piece. And in the world lines came from the saddle point of the world lines. And in the Wilson loop calculations comes from the, so world line, this is the saddle. And in the spool, this comes from the highest weight of that SL2 representation. But then we had these one loop factors. And in the world line, these were fluctuations about that geodesic. And in the Wilson spool, this came from summing over the descendants of that within a given SL2R representation. Okay, and then the two loop shifts the mass to this parameter, and it was completely independent of gamma, which is thankfully had to be the case because in the Wilson spool this was just something fixed completely by the Casimir. It had nothing to do about where the Wilson loop sat. Okay, so where do I have space to write? So looking forwards, we have focused a lot on these torsion-free quotients, and that's because we have a lot of control over the torsion-free quotients. And if it's of interest, I can say why things fail for the non-torsion-free quotients, or I can talk a bit more speculatively about other things such as Virasor T, QFTs, and things like that. Which direction would you like me to go? It's a choose your own adventure at this point.
I choose the speculative.
Okay, speculative, good. So this is something that we have just now started working on. So in some sense, this is both an advertisement, but also a strong asterisk that there are lots of things that we don't quite understand yet. There is a lot of interesting mathematics about why the non-torsion-free quotients fail. So if that is something that you're interested in, come find me afterwards. But okay. So good. So matter in the Virasor TQFT. So as we have discussed several times here, quantum gravity in ADS3 it's perturbatively equivalent to this Chern-Simons theory. It matches the level of the actions, and then we can also start calculating one-loop things about a given flat connection. But of course, it's non-perturbatively inequivalent. And part of that is, for one, we expect that quantum gravity needs to have a sum over topologies, which we can always implement by hand. But even on top of that, it's known that the moduli spaces of these theories just don't match, that the moduli space of flat connections is not in correspondence with the moduli space of invertible metrics. And so what you have to do is you have to construct a projector onto the moduli space that corresponds to invertible metrics.
So flat connections are same as, modular certainty is same as solutions to Einstein's equations?
No, here I'm thinking flat connections as flat connections of the SL2C Chern-Simons theory. And then I want to say which ones of these correspond to invertible on-shell metrics.
But flat connection solutions to the equations of motion of that SL2C Chern-Simons theory?
Yes.
So naively would be the same as solutions to Einstein's equations?
Naively, but of course, like there's the classic example that A equals 0 is flat, but yes.
Got it. But
Yeah.
you're saying that the phase spaces of the two theories. When you say moduli space?
Yeah.
That's
Phase space, yeah. So we want to project in some sense onto a module as part of the moduli space that corresponds to phase space that corresponds to the phase space for invertible metrics. And it's not entirely clear that this should be something possible, or that it's in some sense closed, or even doing so is a nice thing to do. But it turns out it is that. So this is, I think, the meat and the progress as made in this Virasor TQFT paper is that they did construct this projector, and it works nicely. In particular, you can isolate off this component. It's simply connected within the phase space of the flat space of Chern-Simons connections. I think they call it.
This work on F1R.
Yes.
I see. So this is what they did, the meat.
Well, this is part of the meat, but this is the starting point of the meat. Yeah. So they isolated this top component of that phase space. It's connected. I think it's even simply connected, and it projects out nicely. And what's furthermore is that they show that the integration over this part of the phase space defines itself a topological quantum field theory. It obeys the axioms of a topological quantum field theory. So you might think that if I had thrown out a bunch of the flat connections, I had thrown out a bunch of the phase space, that some of the rules of topological quantum field theory of the Chern-Simons theory stop making sense. That maybe they're not closed underneath this projection. But here they happily show that, at least for ADS3, that indeed just integrating over this component of that phase space results in a topological field theory.
Which is the simplest topology in which these two things differ?
Yeah, good. I think actually S3. I think they find something that I think they have a divergent integral for S3. Whereas I think, for instance, if you do the Blau and Thompson, you might find something non-infinite on S3 for just working about the zero connection in Chern-Simons theory.
So if we were just in global ADS2, what is it, 3? With ADS3, yeah.
Yeah.
So global ADS3, both methods will just give the boundary.
Yeah, so good. So yes. For globally hyperbolic manifolds, they seem to have no problem evaluating this path integral. When they work on what they call off-shell manifolds, so these things will be like S3. It's not hyperbolic, but they can still use the rules of TQFT to try and apply there, and they find answers that seem to not make sense.
I don't know enough about this, but even through globally hyperbolic manifolds, don't you get extra, isn't the phase space in the chunk size thing bigger?
Yeah, so I'm talking about projecting onto.
Oh, after projecting on.
Yeah.
No, I was asking about before.
Okay. Well, then yes. That.
So just if you look at, I don't know the story well, but the fact that you're in globally ADS2 gives you some boundary conditions, I suppose, of your Chern-Simons fields.
Yes.
That's it. And then you look at all solutions to those equations of motion with those boundary conditions. If we were in gravity, we would get only boundary gravitons.
Yes.
And here you get more. Is that right? I mean, before projecting.
Yeah, that's right. Yeah. There's because there's multiple possible flat connections there. I mean, yeah.
So that's very concrete.
One way is, just consider a compact topology of a spatial section. So that's like G-2 surface. Like industrial TKFT will tell you that's a Teichmüller space.
Mm-hmm.
How will the Teichmüller space come about if you have just SL2C flat connections, right? It will have some non-compact. I mean, it will not have that nice structure. Okay.
Yes, that's also good. That's also a good example.
I mean, as far as the boundary is concerned, it will be boundary gravitons in most cases. When you have compact, then it's kind of very fun, very particular thing.
But say we just do topology of ADS, global ADS3, then there's no, it's just the same. No? Just boundary
Because
Yeah.
it's the disk, right? It's just the disk. Spatial section.
Okay. So there is no issue. It's only when you have a higher.
Yeah, I think yes.
Yes?
I thought even there it wasn't very well.
I mean, there may be some on-shell, off-shell. Off-shell clearly get out of fields. But he's doing phase space here, on-shell. Of course, yes. Yeah.
You're looking at the classical phase space.
Yeah. Written kind of way of doing it. First constraint.
I will also mention that there are still, when I say it satisfies axioms of TQFTs, I mean, of course, there are different levels of detail that you can get into. For instance, you might think that if I had an ideal tessellation of my manifold and I had some crossing rules for how I break up these tetrahedra, that this should be independent of that. Turns out the VSOR TQFT is not. So in some sense, there are some rules that you might think were reasonable for topological quantum field theories that it's still a bit hairy with. However, sort of the basic surgery rules that you would use to evaluate, say, link invariance and things like this, it does obey those. So when I maybe should put an asterisk here. But there's still some things to figure out there.
Sorry, just a basic question.
Yeah.
I mean, if I just think in terms of path integral, I would have to do a path integral. Let's say even modulo this issue of
Yes.
mapping of Chern-Simons to 3D gravity.
Yeah.
Let's say that I'm not worried about too much, but I'm just worried about these off-shell configurations. Right?
Yes.
So I do have to integrate over those, and on those, a priori I don't seem to have a formula for matter, right? So I would be then stuck there.
Yes.
But here, in then thinking about this way, the phase space and so on, somehow you can fix that.
Yes,
issue, or-
I think so. We have a claim that we have a way of addressing this, or at least we're working towards that. So I mean, essentially, yeah.
But the idea would be that you have something different from the usual path integral formulation of Chern-Simons.
Well, the idea is that you have to alter the phase space of the Chern-Simons theory once you start including matter, right? So if I can imagine, yeah. Let me just actually get to what we're trying to do.
Before including the matter, you will not need the usual path integral, which will allow A equal to 0, etc., etc.
Right, you have to integrate over instead this top component of flat connections.
The projector and the
Yes.
path integral. Okay,
Yeah.
so that's the new definition.
But this top component was, if I understood right, just for on-shell, for phase space, right?
Yeah, that's right.
I think Sandeep was talking about off-shell integrations.
Yeah. But that's what you're saying. You do the path integral with some additional projectors.
Yes, that's right. Yes. Sorry.
Projectors defined even off-shell.
I believe so. I mean, I think. Sorry, it's.
I thought you were saying the components.
Yeah, no. I think. Sorry. Yeah, I should. I think. Good. I think these guys are never actually doing a three-dimensional path integral, right? So what they're doing is they're constructing phase spaces and show that they obey the axioms of TQT, and they evaluate these three geometries using surgery. Yeah.
Yeah. So the two ways of quantizing.
Yeah.
Right? You can try to quantize the full theory and then put constraints, or you can constrain and then quantize that phase space.
Yeah, so-
this is that approach.
Yes.
It's
So
not really the
This
market
has to be integrated over. I mean, this has to be. I thought what you're going to do is you're incorporate matter in it. Right?
yeah, so we're going to do it, but in this constrained first way. So we're going to actually look at the phase spaces of so how you alter the phase space of this when you include matter.
So just to make sure, sorry, so you constrain, you get some phase space, maybe I don't know what Teichmuller space, something or the other.
Without the matter, it's a Teichmuller space. Yeah.
Is Teichmuller, and then with the matter, okay, maybe it's more. Anyway, then you add the matter in this phase space.
Yes,
because you have to add the phase space of the matter, which is
Yeah.
now infinite dimension.
that's right. Yes,
These two things react.
yes, that's right.
Then
Yeah, so-
you
so
quantize that
okay.
whole. That's
Yeah.
the way you do it.
Yes,
Okay.
that's what we're working
So-
towards.
So you will not just borrow this
No, we're not.
finished result.
No,
You have to
no,
like
no,
go
no.
back.
We have to go back, yes, because again, ultimately, the way that these guys work is they work on the phase spaces of these classical solutions and isolating the components of those phase spaces, and so we have to also work in that, at least to how well we understand this. This is also still pretty preliminary.
No, but no matter how you do it, should this not be a basic issue that on official configurations one doesn't know how to do matter? Determinant. Should this not be a basic obstacle to this? I mean, it shouldn't be that you look at it in some other point of view and you overcome it, right?
No, I mean, I think
But even here, once he takes the back reaction of the matter, even on chain, the
it's
space will no longer be reduced.
yeah, it's in some sense.
Even in the phase space way, you'll have to do that.
In some sense, I'm going to be worried about calculating expectation values of things, right?
You can-
And in that sense, I want to find what are the rules of this phase space when I include the matter in there.
Sorry, a logistical
Yeah.
comment, we can have exactly 5 more minutes.
Okay, then I have 5 more minutes of speculation.
So maybe we can give Jackson 5 minutes of questions to finish this.
I really want to caution that this is something we have begun working on. We have some ideas and we have some like preliminary promising results, but there are lots of things that we don't understand, and hopefully we can work this out. But once we start including matter into this, we can think about doing this first perturbatively, start inserting single particle states, 2 particle states, whatnot. And perturbatively, the insertion of a point particle would be looking at the moduli space of this, but now with a conical deficit. And so your flat connections need to pick up some holonomy around that conical deficit. Now, the intuition from our Wilson spool is that once I know this, the summing up of all these guys would be that log z of this matter would be something like a 1 over n summing up all these in particle insertions, which again is something just a statement about both statistics of these, that they're bosonic operators. However, there's something that kind of interesting happens because we have to actually consider what it means for this moduli space when we start including the conical deficits. In particular, there are limits of the moduli space, sort of the boundaries, if you like, of the moduli space that we have to consider, which are the limiting points. And the limiting points are precisely the points where if I say I have 2 conical defects, what happens when they come close together? So these are the boundaries of the 2-particle moduli space. And we have to specify a rule for that. So this is also known as compactifying that moduli space. So the compactification that we're going to work with, and it took us some time to come up with this because there's various consistency conditions that you need this guy to satisfy, is that the conical deficits, well, we originally thought that the conical deficits should just add, but actually, it seems that the most sensible thing is that corresponding to each conical deficit, there's a associated conformal weight, HI, that is related in a nonlinear way that I can't recall off the top of my head. But to each conical deficit, there's an HI, and actually, when I bring these two conical deficits together, the HIs should add. So this is some nonlinear back reaction of the conical deficits. They don't just add, but they actually have some actually nonlinear relation to each other. And this seems to be, as far as we can tell, the right compactification of this moduli space. But there's been some discussions with Lorentz, and maybe this is, I don't know. We'll see. But this is one that we're working with right now. And it seems that once you do this, then you can start evaluating these one-loop determinants in this following way as a sum. And everything seems to work out quite nicely up until a certain point. So it looks like naive if you could do forever. You just keep adding these guys up forever. Then this one loop partition function would be also one loop exact in G Newton. But actually, this is not the case. And what happens is that
Very good.
Yeah.
You can check that classically, right? This HI,
Yes.
this HI.
Yes.
It's the solution.
Yeah. This would be the case if I could continue this compactification for all n. But actually, what you find is that when this n gets to be an n max, such that n max times h. So I'm going to take all these guys to be the same because in this formula, it's all the same particle appearing there. N max times h is C of Brown-Hinault over 24. And this is the black hole threshold. And what happens is that actually find that much like we saw before in 2D, where the character of the SL2R element can shift from being this elliptic to a hyperbolic element. Here, the holonomy of your flat connections shift from being elliptic to hyperbolic. And this, in 2D, what we had seen is that shift told us that actually we did not have a conical deficit anymore. We had a geodesic boundary. And so the interpretation here is the exact same. Somehow these guys have coalesced, and now we have a geodesic boundary. And so this, I think this is fascinating and very exciting because this tells us that it looks like we formed a horizon. And so our slogan for this, of course, there's a lot of things that we haven't finished, but it seems that the Wilson spool acts nicely up to the black hole threshold. And then at that point, everything breaks loose. We're still trying to make sense of how to evaluate things beyond this. We need, in some sense, I need a new rule for compactifying that moduli space. But we can do things numerically. I can't say very much on this because the grad student is working on this and he understands this much better than I do. But numerically, it seems that if I continue adding more and more particles, I can evaluate the leading contribution to the holonomy, and it seems that it wants to scale with an area. But the coefficient is, so maybe I'll write this down, S1 cross D, VTQ of T plus matter. Looks like it wants to be, or at least in this case, a length with a coefficient that is not fixed yet because we're doing this numerically. So I think this is a very, very vague advertisement for work that will hopefully be out one day in the future. But it seems that the VRSOR TQFT knows about this back reaction in a very cute way. And it's captured in terms of this SL2R holonomy in a very cute way. And the Wilson spool continues to work in the ways that the naive Chern-Simons theory told you it would up until the black hole threshold. And then all hell breaks loose.
You're saying there's no binding energy expressed in terms of H.
That's right.
Isn't that very ungravitational?
Well, we were thinking that we were thinking that this was natural from the CFT point of view, and then that the nonlinear relation between the conical deficits was like the statement about the binding energy. That
from the CFT, I think there's no anomalous energy.
Yeah.
Why is that much?
No, but sorry, we're wanting the opposite compactification, where instead the canonical deficits don't just add simply. It's a conformal dimensions that add simply.
You were saying it doesn't just add, right?
Yeah. So
It will not add. But I'm saying there is no effect of the other guy on this. For this guy, it will just
because
add.
everything is locally ADS.
Everything is hyperbola. There is nothing.
Because it's 3 dimensions doesn't really happen. That's the point.
Yeah.
okay, that's my end point, by the way. But we can also continue talking. But yeah.
Time for one or two quick questions. At some point, this room will be taken over by
But just going back to this, are you saying that if you put one operator and another one, that there are no singularities in the FP? Because H1 plus H2.
Yeah, in whatever CFT is,
Yeah.
right? The CFT is a bit complicated. Right? It's, right? Little constructed.
Yeah. So. Yeah, actually, so maybe I should also be a bit careful right now. So we are, yeah. Right now, what we have been working with is chiral gravity, which is only one half of this. And so actually the H's need to be quantized, which is one of the reasons why we need to have these guys add. So maybe if we go to non-chiral gravity, then we're allowed to pick up
You're
anomalous.
just not allowed to have anomalous dimensions.
Exactly, yeah.
Because spin have to be integer.
Yes.
Okay,
So
there it's clear.
So maybe if so our Tory model is this chiral gravity. Maybe once we uplift to non-chiral gravity, then we'll have a different rule for the compactifications that is also possible. But here, this seemed to be the only sensible way forward. Yeah.
What is, now I'm totally lost if you're going to have questions. Your bulk theory was Chern's, was
It's like
first constrained and constructed some phase space.
yes,
That was your bulk theory.
that's the bulk theory. Yes.
And why was it chiral?
So in some sense, we've put everything into k left and turned k right to 0.
Does that agree with the phase?
It's certainly so. There's a lot of reasons why you would not think this is a sensible theory of gravity, but certainly you can play all the same Vier-Store TQ of T rules. You can isolate this component. It still defines a nice TQ of T. You can work with the phase space, and it just happened to be the first thing that we tried. It as a simple step. Of course, if you're really interested in talking about ADS3 gravity, you would have the non-chiral. But within the chiral, this gave us this rule of compactification.
Sorry, I remember this is slightly differently. So when I tried to do this just ordinary, I was just putting a hyperbolic metric on a disk with 2 conical deficits. That's it.
Yes.
And the conical angle did add up, and that gave me an anomalous dimension.
Yes.
Right, because the angles add up and the HS, and then I could check that from CFT that indeed, I think I did some conformal block type calculation. And I could see that indeed is the anomalous dimension.
Yes. Here we're specifying what it means to bring these guys together, how to fuse them into a single conical
No,
deficit.
but the geometry should tell you that, right?
No, but again, there might be some binding energy that goes into that, right? There might be, or another way, there might be a back reaction might bring these guys together.
So what is the metric? The metric is locally not hyperbolic then?
No, the metric is locally hyperbolic.
Then I think the angular deficit just adds up.
It should, because if you go very far away, it should just add, right?
Yeah.
So I mean,
Maybe in terms of H, you don't add.
it might, yeah.
It doesn't mean because h times h minus 1 is mass, right? And deficit is mass.
Yeah.
So that's actually what I thought you were saying.
Yes, I got it
But
back
no,
first.
No, but
But
here, from the CFT point of view, it was very clear to us that the H's had to add because the H's were quantized. Yeah, so it might be
from the CFT side and bulk whatever it is.
Yeah, so it might be the case that actually that there's a breakdown of the map between geometry here in the chiral gravity case. That indeed, and once we go to non-chiral gravity, that we have to work with this different compactification.
Because at least from the geometry point of view, if you just look at the hyperbolic,
Yeah, I mean,
think angles
yes.
add up.
Could I ask a perhaps related question? In Lorentzian ADS,
Yes.
do you have, do things go around? I put a big mass in the middle, and I have it. I look at JD6. Do they do orbits? I mean, do you have attraction? Is there some sense in which things are attracted in 3 dimensions? If I put a mass here, do I get orbits around it, for instance? Is there a planet, sun kind of thing?
Because for that we need geodesic, okay?
Yeah.
Or a probe.
Yeah.
The near the conical that will not be geodesic. Just the point. You need to
outside a BTZ black hole,
Yeah, some horizon bits. Yeah, so not the black hole, right? You mean the conical thing.
Conical, I don't care either.
No, wait,
I just
wait,
see,
yeah. I think outside BTZ black hole you will have all this. No, you don't think so?
Yeah, of course. I mean, it's a geodesic, right? The horizon is a geodesic.
You will have all this.
So there's some sense in which things attract each other, right? Even in 3 dimensions.
Yeah, I mean, that's sensible.
It makes sense that you have
Yeah.
Kepler's law.
Yeah.
Yeah,
That should give rise to anomalous dimensions, that attraction somehow.
then yes, okay. It might be the case again that once we're non-chiral, then you have to choose a
I
different.
think this may be the Lorentzian version of what I'm doing.
Yeah. But yes, so in this first iteration, that we have to make sure that the conformal dimensions don't pick up anomalous dimensions. But it might be that you have to choose a different one.